Hello again. We're going to pick up where we left off. Now we're getting into section 4 of chapter 4. So I want you to think back to this idea of pure water containing equal concentrations of what two ions? What two ions does water separate into? Well, I hope you remember that it is the hydrogen ion and the hydroxide ion. Pure water is a special substance. It has a lot of properties that are unique to it, different from other things that have similar similar formulas to it, or different or like similar states of matter to it. It's just unique in a lot of ways. So its equilibrium expression, the way that we describe how much of its products form at equilibrium, it gets its own name. It's called the water dissociation product, and it gives its own symbol of Kw. Instead of just Keq or Ka for acids, Kb for bases, it's just Kw for water. Now, the equilibrium expression is Kw equals the hydrogen ion concentration multiplied by the hydroxide ion concentration. And again, the brackets around those ion symbols are expressing the word concentration, how much of it is in solution, which only includes the product side of the ionization equation, not the reactant side, because we would normally put the products over the reactants, but for Kw, the reactant is water itself. And so the concentration of water in water is always 100%, which makes it a value of 1. And so it wouldn't do anything to the math to take what's already here, the hydrogen ion concentration, multiplied by the hydroxide ion concentration, and divide it by 1. That would do nothing. So Kw is simply this. Now, experiments show that the hydrogen ion concentration and the hydroxide ion concentration in pure water are equal to this value, 1 times 10 to the negative 7. It's very, very small, but it is measurable. And it has a unit of molarity. That's the chemical unit for concentration, symbolized here by a capital M. Therefore, Kw always has this value, 1 times 10 to the negative 14, because we need to remember in pure water, hydrogen ion concentration is equal to a hydroxide ion concentration. So 1 times 10 to the negative 7 times itself again is where we get this 1 times 10 to the negative 14. But in an acid, the hydrogen ion concentration is higher, and in a base, the hydroxide ion concentration is lower, and that's reversed. Oh, I'm sorry. In an acid, the hydrogen ion concentration is higher, the hydroxide is lower, and in a base, that's reversed. But the product of how much hydrogen ion and how much hydroxide ion, no matter if it's an acid, base, or neutral, the product always comes out to this value, 1 times 10 to the negative 14. It's just that one goes up and the other goes down, or in pure water, they are equal with this 1 times 10 to the negative 7 value. So if the hydrogen ion concentration increases, then the hydroxide ion concentration must decrease and vice versa. Okay? So if the hydrogen ion concentration is high here in this first blank, that would be an acid. And if the hydroxide ion concentration is high in the second blank, that would be a base. So I'm going to give you 4 problems here. We will do these back in class, but there's just a simple algebra thing you're going to do here. It's simply plug it in your calculator in the right way. We'll remember to use some parentheses since we have some values in scientific notation, but this is a little bit of math. It's not even as difficult as the math you did the first time we had some math in chemistry, but we'll work on that in class. Okay, now, concentrations of ions are often really small numbers, and we express them in scientific notation, which remember is a digit, decimal, the rest of the important digits, times 10 to some exponent. Since these numbers can be cumbersome themselves, chemists adopt another way to express hydrogen ion concentration, and that is the pH scale, simplifying the numbers of hydrogen concentration into a whole number or a close to whole number value. So the pH scales allows hydrogen ion concentrations values to be expressed more simply using common logarithms. pH equals the negative log of whatever the hydrogen ion concentration is. Whatever value that is, negative log of that value would give the pH. This calculation is simple to make using a scientific calculator. In your head, not so simple, but using a calculator, very simple. By typing in the sequence, you start with the negative sign, and then you push the button that says log, and then you type in the value that's given for the hydrogen ion concentration. Then you just hit enter after you close that parentheses. So with that, you could go to the previous slide and figure out the pH for A and D with the given hydrogen concentrations from there. So on the pH scale, a neutral solution is pH of 7, an acidic solution is pH less than 7, and a basic solution is pH greater than 7. And the logarithmic nature of the pH scale means that a change of one pH value is actually a times 10 change in ion concentration. So if one acid has a pH of 6 and the other acid has a concentration or a pH of 5, that lower in value acid, pH of 5, would actually be 10 times stronger than the pH of 6. Remember, pH strength, acid strength increases as pH goes down. Base strength increases as pH goes up. Now, sometimes it is convenient to express the basicity of a solution on a pOH scale. Instead of just talking about it in terms of a weak acid, you can kind of flip the script and be like, well, that's actually a strong base. So the pOH scale is just another way of looking at the same info. pOH and hydroxide ion concentration are related just the same way as pH and hydrogen ion concentration. Therefore, the same equation can be used of pOH, like pH, is equal to the negative log of the hydroxide ion concentration, in the same way pH is equal to the negative log of the hydrogen ion concentration. pH and pOH values also have an inverse relationship. You can see that on the scale from the previous slide. So neutral is still the same. Even with an inverse, they meet in the middle. pOH values equal 7, but an acidic solution has a pOH value greater than 7, whereas pH was less than 7. And basic solutions have a pOH less than 7, where pH is greater than 7. And this is the brutal part about acid-base chemistry. It's all of these like inverse opposites and just keeping all that straight. So put in the work to really get, for me, I remember one set of info, and then I just remember that for the other set of info, it's opposite. For others, they do it differently, but that's just for me. I get one set of info memorized, and then I go, okay, and the other is the opposite in every way. So pH and pOH values are always connected by this equation. pH plus pOH will always equal 14. In the same way, from this equation right here, that the product of hydrogen ion times hydroxide ion always come out to 1 times 10 to the negative 14. If you take the negative log of that, it gives you 14. So it's kind of connected in the same way. pH, pOH, hydrogen ion, hydroxide ion concentration. And then again, we're going to have some more practice with this. We're going to do some equations with this. You're going to be using this little square to help start you with this problem-solving process. But on your test, you won't have this exact diagram. On your test, I will probably give you some help with these equations, but you won't have this exact diagram. You need to let this diagram assist you in the practice. So if you don't practice, you're not going to get any help. You're not going to get any practice in getting used to using these equations. And even if I gave you all the equations on the test, without practice, you wouldn't know where to use them. So you'll have this square in your notes as we practice with worksheets, but you won't have this exact diagram showing you exactly when and where to use these equations on your test. You need to get used to that. That's what you need to work on with your problem solving practice, is when and where to use an equation appropriately. So our last conversation in this chapter is about buffered solutions. So for many things, including humans, many living things, the internal pH of the body is very important for life. Gastric juices from your stomach should have a pH of very acidic because they need to break things down. But those same acids should not be anywhere else in the body, because then you're breaking down your own tissue. Whereas the blood needs to have a pH in a range of 7.1 to 7.7 to allow blood to do its job of transporting oxygen and transporting CO2. And then metabolic processes produce acids. So the body has a complex system to maintain healthy pH levels where it's needed. To maintain pH levels within such narrow limits, very narrow pH windows, living organisms produce buffers, solutions that resist changes in pH when limited amounts of acid or base are added. So a buffer is a little bit like a sponge in a way. Like if a little bit of acid or base is added to a system, the buffer can kind of absorb that acid or base, keeping the overall pH of the system from changing. However, just like a sponge, if too much water is added to a sponge, it can't absorb anymore and it leaks. A buffer can only resist that change in pH so far. If you overwhelm it with too much acid added or too much base added, it can't do its job anymore. And so we can look at this kind of effect on this chart, and this is something we'll talk about in class. I'll kind of pick your brain on this chart. A little bit of an ACT practice question here. So buffered solutions, the buffer itself, the thing that's in the solution, is always a mixture of a weak acid and its weak base. Not just a weak acid and some other weak base that's random, but the weak acid version and weak base version of the same compound. They're always a conjugate acid-base pair. Two substances where the only difference between them is one has the hydrogen ion, the weak acid, and one does not, the weak base. The combination of a conjugate weak acid and weak base resists changes in pH by reacting with any hydrogen ions or hydroxide ions that are added to the buffered solution. So let's look at this situation. So right in the middle, we have a buffered solution. We have HAN, something with a hydrogen ion, that's the weak acid, and we have AN negative, that's the weak base. Okay? When both of them are present, that's a buffered solution. So the first scenario is added hydrogen ions from a strong acid. They're going to bond to the weak base anions, producing more of the weak acid molecule, which can't lower the pH much. So the effect of adding an acid, adding a strong acid to a buffered solution, the effect is just more of the weak acid is created. And a weak acid is not going to change its pH very much because it's weak. So a buffer takes the addition of something strong and turns it into more of the weak version of it. Okay? Same thing if hydroxide ions are added from a strong base. So added hydroxide ions from a strong base pull hydrogen ions off of weak acids, producing more of the weak base anions and more water molecules, neither of which can raise the pH much. So the effect of adding hydroxide from a strong base is that more of the weak base is added or is created. Therefore, the pH doesn't change very much. Now, as soon as one of those two things runs out, if the weak acid runs out because so much a strong base has been added, then the pH will change very quickly. But as long as there's both versions, the weak acid and the weak base of the buffered pair, as long as they are present, they can resist change in pH by effectively taking the addition of strong acid and turning it into weak acid, and the addition of strong base and turning it into weak base. Okay, well, we will practice. Actually, there's not much practice to do here with this stuff. This is mostly just for vocab and understanding the principle. But that's it. That is the last video for your chapter.